about CNN acceleration on FPGA. So first of all, what is FPGA? FPGA is a field programmable gate array. It's an integrated circuit contains of a lot of semiconductors, and it is designed to be reconfigured by customers in the time of usage. Usually, it can be described in HDL, hardware description languages like Verilog and VHDL. And it's important thing that we don't program FPGA, we just describe the architecture using these languages. Also, it can be designed on a lot of abstraction layers from the lowest logical gates and or not up to uh, higher things like arithmetical logic unit or DPU, deep learning processor unit. Uh, Also, it can include on-chip memory. Uh, it can include simple flip-flops or something more complex. And sometimes it is used to create ASICs. Now, what is CNN? CNN CNN stands for convolutional neural networks. Neural network is a graph with connections and weights of every connection. It consists of a lot of layers. You can see on the picture below that layers can be some operations, convolution, ReLU, pooling, or normalization, batch normalization, instance normalization, or something else. Usually, CNN is used uh, to process videos or images in real time, or simple process videos and images. And we use it in classification tasks. For example, on the image we have on the input some image car, and on the output we have the word that describes that this is a car. And this particular neural network is for classification different kinds of cars, truck, bicycle, something else. Convolution is the main operation in convolutional neural networks. Convolution is math operation on two functions, and the result is the third function. And this third function shows how the first function modifies the other one. On the picture, you can see that we use in convolution process we use some metrics. In image processing, we use the image as a matrix, m over n, and we use small kernels. It can be from one up to many kernels, 3 by 3, 4 by 4. It have to be square, and the result is some smaller metrics that shows some features of the input image that is get by applying the kernel. Now let's speak about most popular approaches of convolution. Uh, we will start from different frameworks. There are a lot of frameworks to deploy our models on FPGAs. OpenVINO. OpenVINO is an Intel project. VINO stands for Open Visual Inference and Neural Network Optimization. OpenVINO is a product for heterogeneous systems made by Intel, and from the very beginning, they used it to accelerate to run and accelerate the neural networks on CPUs and GPUs from Intel. And then after Intel bought Jurassic Corporation, it is also possible to use OpenVINO on the Jurassic FPGAs like the 10 Nano or some else boards that you can know. Mipsology. Mipsology is a startup. This startup have a product called Zebra. Zebra is a deep learning compute engine for neural network interfaces, and this is something like OpenVINO, but for more platforms, because OpenVINO can be used only for Intel products. So they told that any model trained on your computer can be deployed using Zebra on different platforms that they support. And their main partner is Xilinx, now AMD, because AMD bought Xilinx. And they told that they have no change, they made no changes in the process. Everything is done by Zebra, and the programmer should not modify his network to deploy it. And they told that accuracy loss is about from 1 to 3%. That is not a huge difference. Now Xilinx. Xilinx is a corporation that have few frameworks to deploy the neural networks on the FPGA. VTSAI is the first. VTCI is a platform that is known from the 2019, and it is a development platform for AI inference on Xilinx hardware platforms. And also, as far as we have Xilinx boards in the cloud, so we can run it in the cloud and on the FPGA. It supports model designed on Caffe and TensorFlow as and the documentation say that PyTorch models can also be deployed on the Vitis AI, but as far as I know from my experience, PyTorch models can be only quantized on this Vitis AI, but there are no known solution how to compile, optimize, and deploy it on the boards. So I don't write this in the presentation. And also they told that the usage is very simple for all developers who are not in embedded sphere. So you need to just add something. You need to add a few imports and few lines in your model on Python to run it on the GPU. That is also a part of VTSAI, but it's a hardware part. And it has a lot of documentation in the GitHub and on the official site. Also, it has an open source part. It's not fully open source because on the very top of each document there is a license that you cannot change the code. You can just read it to analyze what problems you have, and you cannot share the code. So it's a little problem while working with this framework. And also the other disadvantage is that it officially supports only 3 boards, but as far as the part of code is open source, it is possible to add more boards. For example, I have been working for 3 months with a board that is not officially supported, but it's very easy to write few scripts and deploy any model on this particular board. And for other boards, it can be um, simpler or harder, but it is possible. And Pink is another framework from Xilinx. It fully open source project, and it let you test your code, test your model in Jupyter notebook using Python language only, and also that deep processing unit that I mentioned before. It use parts of VTCI, for example, this DPU, and it has 8 officially supported boards that make it maybe simpler for beginning, because these boards are cheaper, and it's easier to work with them because you only need to change the chip in the Jupyter notebook settings from the CPU or GPU to FPGA, and add some more lines in your code, and also add some more libraries in imports. And also it's easy and fast to deploy models, but it's not a real solution and not a real product, because uh, these approaches will be um very slow, and they it is possible only to test the neural networks in such way. Okay, now let's talk about low-level approaches of calculating convolution on the FPGA, because convolution consists of some operations, and we can change this operation uh, matrix multiplication using some functions as to call. We can reduce our input image matrices and kernels to matrices that can be multiplied, and repatch operation to repatch the output matrix, and we will get the result of our convolution. So the pros of this approach is there are a lot of uh, there are a lot of ways to accelerate matrix multiplications, but cons of this approach is that it needs additional operations into call and repatch that take a lot of time, and this approach cannot be can not be faster on some boards. For example, this it says for FPGA, if we will use a simple matrix multiplication on FPGA, it will be much more slower than the same approach on the GPU, because GPU is the best for matrix operation over on matrices, and for matrix multiplications. And CUDA kernels has these SIMD approaches, single instruction, multiple threads, that helps to accelerate matrix multiplication on the GPU, but FPGA have some different structure that makes it impossible to use simple matrix multiplication. So we have to use quantization. What is quantization? Simple model without any changes, have only float 32 weights and layers that operate with these float 32 numbers. So let's try to reduce our float 32 to int 8 or int 16 or float 16, uh, because we need a lot of power and a lot of memory to save float 32 numbers and that layers. Um, by reducing our numbers to int 8, the result model will be faster. The and model will be not so weight, and we will save the same accuracy as before. How to do that? Every framework have its own approach to quantize. For example, TensorFlow that you may know can have their its own supervised and unsupervised post-training to quantize the model, and Xilinx with its Vitis AI have part of this Vitis AI called Quantizer that help to reduce such numbers. It also a post-training, and for each model for PyTorch, TensorFlow and Caffe models, the process and input data will be different, but the result is quantized model that you can compile and deploy on the GPU on the FPGA. And also it is necessary to transform not only weights but also operations and lawyers. And That's why when you write any model that you want to deploy on FPGA, you need to use only that lawyers that are supported by the framework that you want to use to quantize the model. It's important thing, and you need to check the documentation before start developing the model. And ABM SPConv, it is accumulate before multiply sparse convolution. It's a very new approach that is from the article 2019 year. Um it is a process that is some have some difference from simple matrix multiplication because they not they don't use im to call and repatch operation. They just use convolution on the FPGA, but with some different. Convolution operation consists of multiplications and adding the result after multiplications. And they found that it is possible to make this operation, to separate these operations and to multiply all needed numbers, and they add them. What is more, they use on-chip memory to cache the results of multiplication. And in the output, we have that if we if we use the same kernel for the image in different parts of this image, the numbers can be the same in different parts of the image. So in the result, we multiply the same numbers twice or three, four times. They have pre-processing of the convolution that calculates the number of uh, entries, each number in the input matrix, count it and sort it in some way, and save these results in the table on the on-chip memory, so that when the model see something like multiplication of two known numbers, it just take the results from the table and don't do the multiplication. On the pipeline, in the on the pipeline, you can see that the time can be reduced up to from 2 to 3 times. And the best in this approach is that they use from 38 to 50% of DSP blocks, and the same about on-chip memory, because all articles about neural networks acceleration and all experiments in the articles use from 98 to 100% of DSP blocks and memory, so it makes impossible to have something else uh, on the chip, but only the parts that use convolution and this approach leave half of board free, so you can use this space to deploy something else on the board. And in this approach, only first applying of the kernel is very slow, and all other operations are faster and faster. And maybe the best for now approach is Vinogradov group of algorithms. Vinogradov, uh, the very first variation of this, the very first iteration of this algorithm called Strassen algorithm, but Vinogradov is the person who accelerate the matrix multiplication from n cubed to n in 2.3. It's much more faster than everything before, and Vinogradov approach was the fastest known matrix multiplication approach for 30 years. And in 2010, math people start to make it faster and faster, but the faster approach is n in 2.36, so the result is not so huge as Vinogradov did. That's why this group of algorithms called Vinograd, sorry. And as you can see on the slide, for 2 by 2 matrix, the naive algorithm for 2 by 2 matrix multiplication, the naive algorithm require 8 multiplications and 4 additions. Strassen version of this algorithm requires 7 multiplications and 18 additions, but Vinogradov required 15 additions. So for small matrices, you use only addition without multiplication operation to multiply matrices. Why it can be faster? Because uh, as far as I know, both GPU and FPGA uh, uh, have more units to make addition than multiplication, and that's why it can be the big deal to it can be very useful to reduce the number of multiplications, even if it will increase the number of additions. And There is no difference in time for FPGA for different designs. For designs that use GEM or Vinograd algorithm, we don't speak about ABM SPConv here because it's from an article that compare uh, only GEM, VTSAI, and Vinograd algorithm. But the big difference is that resource utilization and power consumption the is the better using this Strassen Vinograd algorithm. And uh, in real life, as far as we use not all FPGA for neural network, but we want to have something else on it. Other approaches can be much more slower. The same about multiplication units and addition units. And for this reason, yes, Strass and Vinograd is the best known approach to accelerate the CNN on the FPGA. And also there is one more algorithm called Coppersmith Vinograd. You can check it. It is more interesting, but it gives acceleration only for such big matrices that are not used now and that cannot. So this algorithm called like universe or something like that, and is not used in our life. So thank you for attention, and have we more time for questions? And uh,
Mhm.
any questions? Maybe something have.
Yeah, I think we have time for some questions. So if you have any questions, just feel free to ask them. You can ask them in chat or you can raise your hand. Or if you don't have any questions now, but there will be something pops up to your heads like later on, then we can also have the discussion after every presentations, because we've got a Q&A session on our agenda as well. Okay, so one last chance. No. Okay, so Mikola, thank you very much. It was
Thank you for
very,
attention.
yeah, it was very inspiring. And now I can think that we can proceed to another presentation in our agenda. And that would be projector camera calibration challenges by Andriy and Yuri. So a few words about our speakers. So Yuri Cobain is a senior embedded software engineer with more than 10 years of experience in engineering and technical leadership roles for embedded and high performance programming projects. And Andriy Husainov is a senior R&D engineer with more than 10 years of experience in software hardware engineering and testing. He has an extensive background in telecom, hardware engineering, and computer vision. Okay, guys, so the floor is yours.
Hello, so my name is Yuri, and today I would like to tell you about structured light as technique for depth reconstruction and on embedded devices. Okay, one moment, please. So first of all, we talk about some existing algorithms for 3D reconstruction and depth measurement. Then we're talking about specific structured light, category of structured light, and how it used for image formation, and then the problems that is faced in order to solve the depth. It's like phase shifting, and technique is phase shifting, and actually the problems that we should solve in order to recover the shape of the object is phase unwrapping. And with some results that we achieved locally here, because right now we are working on prototyping some 3D scanner using actually structured light technique and especially phase shifting method. So in general, we can divide 3D reconstruction in two categories. It's active and passive methods. And active methods is like contact methods that could be used like physically to measurement the depth of the target object. Some very popular nowadays time of flight a technique that uses this time of flight camera sensor that actually measured the distance to the object between sensor, but it's the idea is we just project some ray on the object and measure the time of reflection to it, and based on it we can measure the very accuracy the distance. But the problem with this method is that the cost of such sensors is quite high, and the resolution at this moment is quite low. And so for that reason, we could not reach very high resolution and detailization. Also, triangulation, like active stereoscopy, when we can do multiple images and then using triangulation to measure the depth of the observed images. And especially what we're talking about is structured light. This method used some specific pattern that is projected on the object, and then camera like captures the reflected image light, and using some specific algorithm to reconstruct the observed image, the observed object. Also, there is another method like modulated light that is continuous and volumetric. Also, there is some passive method that actually do not interact with the object somehow. They only use raw images in order to analyze and reconstruct the image based on those object based on those images. It could be also neural network approach using some very CNN with very deep convolutional neural network. Also stereoscopic system with like very simple, it's stereo pairs cameras. But the stereo pairs cameras, it's quite cheap setup, but the accuracy is not quite good. So as example of some of the technique, for example, is car with a lidar, stereo images, or some light modulation. So structured, so there is a lot of types of structured light algorithm, and in general, they can be divided on sequential projection and continuous varying patterns like single shot, rainbow TD camera, some stripe indexing and grid indexing patterns. And based on those methods, there is a lot of hybrid methods that combined different method mentioned above in order to achieve some of the best performance for particular cases. So the our focus is phase shifting algorithm, and it's related to sequential projection. Actually, there is a binary code algorithm, gray code, and phase shift. Like the main algorithms in this category. So binary code, the main idea is, so actually what we have, the system is quite simple. We have structured light projector. It should be some digital projector. The best case is some industrial projector based on LCD matrices, because it's the constructed images is the best quality for such setup. Also camera, the best case is also some industrial camera with a very good optic but it could be also some cheap web camera or another one. And but idea is, so our model is, first of all, what I will show, it's a mathematical model, and it assumes that projector is parallel. It means that we project the patterns like parallel lines that does not divorce in the distance, that actually between different angles we have the same pattern. And orthogonal camera, that means that we don't have some perspective distortion. And the idea is we project some known pattern on the object, then capture the reflected image on the camera, and knowing the parameters, for example, during calibration of camera projector, the angle between camera and projector, we can then use different technique in order to reconstruct the original object. For example, binary code uses at least, for example, 10 patterns in order to project on the image. Each using 10 patterns, we can decode 2 in power 10 pixels, and actually then we can uniquely find correspondence between projected image pixels and captured pixels. And then using triangulation, find actually our distance from the camera to the object in the scene. Binary gray code is like the same approach, but we have different decoding and encoding technique. So actually, phase shifting is a little bit different technique. It uses periodic sinusoidal or cosine signal in order to project in the on the object, and then also we capture it, but the uh, decoding procedure is a little bit different. Actually, we need at least 3 or also 3 images are enough in order to achieve a good result. Because, for example, for binary and gray code, as I said, for example, to decode 1000 by 1000 image, we need at least to project at least 10 images. So phase shifting, in general, this setup is the following. As I said, we have projector, we have camera, we have some ambient light, and we project some known pattern. It's in our case, it's cosine or sine signal on the object. We project 3 of them with a different phase shift. At least it should be 3, but in our case, we use 4 step pattern. And then we capture the reflected image by the camera, and distortion of this phase alpha x y, it's like the coordinate of the pixels, is decoded actually by distorting, and then using some algorithm we can decode this depth in order to receive the 3D model. This actually not 3D model, but actually depth. So it's like the main idea. So when we have an important moment for the phase shift, that we need to know the reference. For example, we have the flat uh, plane. We project some unknown pattern on it, and we know how it looks without any undistortion, without any distortion. Then when we have some object on it, then the reflected capture is different, and then it's introduced some phase shifting in the captured image, and we can then decode this signal in order to receive this phase shifting that uniquely decode the depth of the object. So image formation looks like I said, we have some n Phrygian patterns projection. We project it on the image, on the object. We capture reflection, and then we form Phrygian acquisition that afterwards could be decoded into the phase that uniquely decode the depth of the object. So there are also are a lot of variation of these methods, like standard and step, double three step. Also, the pattern itself could be not always sinusoidal, but another signal that is periodic in time. On this method, we have some constant pros. So in our case, we use like standard and step phase shift algorithm with n equal 4. It's like the more robust and the most simple method, and it shows quite a good result. But others are more complicated and required some better like equipment in order to project some good patterns. So standard and step phase shifting looks like I said we have an sinusoidal signal that is shifted by equal step period, and then we project those patterns on the desired object, capture the result, and using like the formula for phase that uniquely decode the depth, we can achieve this. We can achieve this actually phase, but one problem that will be mentioned. So actually, this is quite simple. We just project and using the reference images and reflected images, we calculate this artank function for each pixel. But the problem is that artank function is defined from minus p to p, but actual real original phase could be the multiplier of p. So we have that call is rapid phase, and this problem could be resolved by some algorithm in order to restore original signal. And so actually there exist several technique in order to restore original phase. It's very common. It's Fourier-based standard temporal phase unwrap. Also, gray code and phase gray code actually don't need phase unwrap in general, because we use triangulation in order to restore the depth, but it could be used as a reference for the this method. So, in general, as said, the problem of phase unwrapping is to find such integer multiplier k in, that should be we should add some multiplier of 2p and add to the rapid phase in order to restore unwrapped phase, and this k should be found for each pixel. So, for example, there is some preconditional conjugate gradient phase unwrap. It's some analytic function that we could describe our expression in terms of Laplacian, and then using fast cosine transform for Laplacian, we can restore or estimate the unwrapped phase. But as we can see, this method is quite heavy. We use direct and inverse cosine transform, and it's also iterative. So we should perform it in a loop and then estimate each on each step if we actually found the solution. And as we see, for example, if the size of the image increase, this problem increase not linearly but we have logarithmic complexity. And but on the other hand, is this like analytic function we could quite precisely restore the original phase, and is for some cases it's a quite good method, but as I said, it's very heavy, and for example for real-time application it could requires a lot of computer power to perform this very heavy operation. So like the looks like, so in terms of algorithms, we firstly estimate our unwrapped phase phi, like our original image, when you calculate the first integer k, and using this equation. So this equation it's a pure mathematical model, but it's straightforward. We just perform discrete cosine transform on original image, multiply it by Laplacian coefficient, perform inverse, and estimate the error that we received with the previous step, and then continue until our we don't actually we don't have any changes with the previous steps. Unfortunately, there is more simple and more quicker approach, but it requires in 2 times more images. This is standard temporal phase unwrap. The key idea is to firstly use low frequency pattern to project. In our case, it's 1 Hertz cosine pattern, and then use this low frequency images as a reference to restore high frequency images. So because this is 1 Hertz images, they it have very nice property that it's not wrapped. It's already unwrapped and quite flat face. And actually, using this information, we could then restore look at the difference between between low and high frequency, restore the original coefficient k in order to find the unwrapping for the high frequency component. But it's also not it's not a perfect solution, because it doesn't work very well for very high frequency when the difference between low and high frequency is too low, it is too high. But there exists some good ratio, and another good approach, we could use a few steps of this standard temporal wrap, for example, to firstly find the phase with low frequency and a little bit, for example, in 3 times or 5 times higher, and then use this higher frequency as a reference for the next more higher patterns. So some result on synthetic data. So actually, we work with some not real images, but images generated in Unity. When all this assumption regarding parallel projector orthogonal camera keeps. And for example, we use this our target board was that's Nano with GPU that have based on Maxwell architecture with 128 CUDA cores, and it has on board very nice Cortex A 57, and actually the result is quite surprising because, for example, the it's obvious of Python was like for mm, prototyping, for quickly prototyping, and then we tried to implement it on the Scholar C and CUDA and C using SIMD extension with multi-threading. And for example, for input images size 124 by 124, we reached quite good result using temporal phase unwrap. It's, for example, it's 1 millisecond uh, for on the ARM processor, and it surprisingly was on GPU it was in 4 times slower, and I think it's due to that Nano doesn't have a separate memory for GPU. It's shared memory. It's all about some memory synchronization and copying. So, and the Fourier-based algorithm BCG shows very like not terrible but expected slower result. And on the CPU, on GPU it is more or less better, but but it's not comparable with TPU. And also some relative errors regarding we tried different Phrygian's pattern, I mean different step, and it show that with the Phrygian pattern actually when we increase Phrygian patterns, sometimes it better. It's also the question how what you should uh, uh, like for each for example, for sphere, it showed such a result. But for example, for a different object, it should be a combination. Should probe what is the best number of patterns to use. And mesh generation actually from this depth map, we can then generate point cloud, and using machine cubes or grid octree based algorithm, we can then create a 3D mesh of the object. And at this moment, this step of our 3D scanner is under development. We're not ready to show it, but hope it will be ready soon. And actually the approach the use cases of such technique. So it due to its the static model of this setup, I mean that projector and camera should be statically and fixed and calibrated, and also the distance that it is very good for short on not too long distance. It's about 1 meter or 2 meters. It could be uses, for example, for for construction of some museum artifacts, and in order to precisely capture some historical artifacts. Also, it could be useful in some retail when, for example, you should to scan some shoes or another a little object. And in medical or dentist, for example, to for restoring the teeth. And but also with that, this method has some constraint regarding the material of the object. It's not suitable for dark object or objects that has is glittering, and also with hair or fur. So, but nevertheless, with this, otherwise, this method is quite after calibration and fix it. It's quite robust and have a very good resolution. It could be even less than. It could be about 200-300. Not nanometers, but 100, 1 divided by 100 meters. Okay, it could be very precisely, and it's, I mean, it's very, it's in times better, for example, than stereo pairs or time of flight. Oh, sorry. So maybe you have some questions.
Please, you can. This is the moment to ask some questions. And as I've already said, if you want to ask some questions during the presentation, you can also do that in the chat or in our Q&A. So just, feel free to ask. And if no, then I think we can proceed.
Okay. Hello, my name is Andriy Husainov. And I will tell you about the actual reality for this method, because what Yuri was talking about is kind of more in theoretical field. But when things come to reality, we need some of the crucial steps that will make it work. So basically, the first steps are to calibrate a camera and projector. To make a stereo calibration for the camera projector pair, to have rotation and translation parameters for the actual point cloud generation, and we also need the gamma calibration. And in the end, of course, because we want to make the 3D model, we need to turn our object. So as it's strange it will seem, but we need also to calibrate turntable to understand how it rotates. I will briefly go through the actual theory about calibration, but I will not spend much time on it. So basically, in our case, we use the pinhole model for the camera and the projector, which actually very simplistic like approach for the describing camera, and we have the camera plane image with its coordinates and world coordinates. And basically for the calibration, we used the Zhang method, which is implemented in the OpenCV. And in this method, actually, the world plane is situated at the beginning of coordinates. So we are assuming the 3D points are coplanar. Also, the same model can be applied for the projector. So we have same pinhole camera model, and also can be used for the calibration, but with some additions, because as you know, the projector is projecting images, not acquiring them. So what we want to get from these calibrations? So we need the intrinsic and the extrinsic parameters, mainly calibration matrix, which consists of principal point, skew, and our focus distance. And the thing is that worth to remember that actually the skew is not taken into account much, for example, in OpenCV, but it can be possible that skew factor has is embedded in the camera. It's actually uh, can be introduced in the manufacturing process when the actual camera image sensor is not parallel to the optics. So in this case, we will have some skew, and it can actually interfere with the our calibration. The next one is the rotation matrix, or the rotation vectors in our case, because to get matrix we need to apply the Rodriguez formula. It will actually describe how the world plane, I mean our calibration plane, is rotated with respect to camera plane. The next one is the translation vector, which describes how the how to translate the image plane coordinates to the I mean 0 point to the world plane 0. And actually one of the most important for our method is the distortion coefficients, because the pinhole camera model doesn't take into account the lens distortion. As we all know, there's the several distortions that are introduced. There are some barrel distortion, some pincushion distortion, and etc. But fortunately, during the calibration with the, for example, calibration toolbox in OpenCV, the distortion coefficients are calculated. At first, during the calibration, we take only ideal model, which is described by pinhole, and then from there we can actually estimate the distortion coefficients. So we can actually undistort our images after we acquire them, and also we can actually make some transformation for the images that we are projecting, because the projector has also a lens system which will introduce some distortions. So in the end, also we will need to acquire the stereo calibration parameters, mainly the rotation translation vector. So we will we will have those parameters which describe our projector rotation with respect to the camera. So we can then use them for our point cloud generation from the depth map. But for depth maps, actually, we don't need to have stereo calibration in our algorithm. It's but for other algorithms, it's also required when we need to triangulate. I guess Yuri was talking about them previously. In the end, we will have to actually not in the end. It's one of the middle steps to make the gamma correction calibration. So the projector luminance is non-linear, linear. So we need to have our fringe patterns that we will project to extract the depth map. We need them like very linear and to have gain maximum information from the pattern reflection. So we also need to account for the gamma effect and actually make some additional gamma calibration. So in our setups, we use a few of the things, and we had a few cameras, some generic cheap camera. Also, we used the Google Pixel 4 phone as the camera went through ADB, and Nikon DSLR was the I would say reference for us in terms of quality. Also now we have in our disposal the Stereolabs Z camera, which is quite good piece of equipment. Is It's actually targeted for the robotics and depth maps, etc. So this camera is very good for us since it has already all the calibration parameters stored in it. So using API, we can get them and just skip the calibration and just get the rotation and translation, I mean, extrinsic parameters for our plane, which will help a lot. Also in our disposal, we have projector BenQ, but it is based on the halogen backlight, and this is a DLP projector, meaning that it uses mirrors to create the our image. So it's not ideal for this application. Later I will describe why. So we went through several setups, and the first one was classic chessboard pattern setup. It's quite common and quite robust, and use one of our methods that we use for calibration uses the chessboard, but it has some limitations. As for example, we cannot do the partial calibration, so all the chessboard patterns should be visible to calibrate camera. Uh, and what we noticed that light should be uniform, so as little ambient light as possible, because when some part of the board is blown out, the calibration suffers very much. So as shown in this image, we can see that part of the board is highlighted, and we had deep in our calibration data because of it. The next setup, we used Charuko markers. Those also available in the OpenCV as a standard, those in calibration tools. And we had the Charuko board on one part of our calibration plane, and the other part was white to project some calibration patterns for projector to be recognized. But it actually yield quite good results, and since the both patterns were coplanar, we could easily calibrate our rig. But the field of view was not good enough for our purposes, and we needed to change something. And in the end, we projected our calibration circles for projector directly to the Chiruko board. So actually what I forgot to mention that the Chiruko is combination of the chessboard pattern with the actual augmented reality markers, and it's very good combination for the calibration purposes. Okay, so we used two methods with some advantages and disadvantages in both of them. The first one was gray code pattern projection, which actually used the standard chessboard pattern. It's quite advanced method, I would say, and it yields quite good results. The other method is ray plane intersect, which actually use the Chiruko markers and the circle pattern to calibrate the projector. So gray code pattern, its method relies on uncalibrated camera and makes use of things like called local homographies that can be found between the projector image plane and the captured image plane, camera image plane. And what is very good about this method that actually calibration of the projector is not relying on the camera calibration. So they are calibrated in parallel because we are finding those homographies between the images, and each row and column of the projector DLP or projector matrix has homographies to some pixel group on the camera. So basically, this gray code pattern method is quite robust in case when we need to calibrate the camera and projector separately, and not and the stereo calibration is the key. So, but it requires quite big calibration board to work properly, and also it requires quite a few images. So the recommendation is to use at least 5 poses, and for each 5 poses we need to take 12 images with vertical and horizontal gray code patterns. So it's quite a hefty amount of images to be taken. And it of course will take quite a time if, for example, camera has very big resolution, as we had with our DSLR. So the second method is ray plane intersect. This is quite different from the previous one, because at first we are calibrating our camera to obtain the rotation and translation vector. And then we are using reconstruction of the plane from the rotation and translation vector to gather 3D points. And we are gathering them by intersecting rays from the camera origin through the image plane of the camera and circle centers of our projected pattern onto the plane in the 3D world, so reconstructed from the rotation translation vectors. So, and when we have those 2D and 3D points, then basically any method can be used for the calculation of the parameters, calibration parameters. The actual disadvantage of this method is that we need to calibrate camera beforehand and then calibrate the projector. And of course, when we have reprojection error on the camera, it will translate to the reprojection error of the projector. But it's quite faster. It requires less images. Uh, Actually, the whole system can be calibrated using only 3 images. But of course, to get more robustness, we need more. And it is quite robust to light conditions, actually. So even quite lit room can be used for the calibration. And as for camera calibration, because we are using the Cherukho board, we can even have partial visibility of the board and still calibrate the camera because of the robustness of the method itself. It's very good if camera should be calibrated when board is has obstacles like some, I don't know, some overexposed, overblown areas by some additional light sources or something like that. This was quite interesting thing because when we started our calibration with Cherukho markers and we generated our calibration pattern for the projector, and by default the pattern is generated using black circles on white background. And when we projected this image onto our calibration board, our camera had very low dynamic range. So basically, our calibration board was overexposed, and we had a problem even with calibrating a camera. So one of the solutions was to make a photo for calibration of camera without the projector, and then project our calibration pattern and make another photo, but it's not quite good. And then we decided to actually invert our calibration pattern and use custom blob detector for the OpenCV circle grid detection algorithm and force him to detect white circles on the black background. Yeah. So with this approach, the camera calibration went without issues, even for the very cheap camera. And as you can see, the result for the undistort were quite pleasing for us. So the image was perfectly aligned, and those we have reprojections for the augmented reality markers, so we could see how the plane is reconstructed. Yeah, and with in the final setup, we combined Cherukho markers and circle calibration patterns, so we could make our field of view more narrow. So it will give us ability to scan smaller objects, since we are aiming to scan some, as Yura said, artifacts and some maybe dental things, and yeah. So in the end, what we got from our projection errors, the gray patterns yield quite a good results for the projector, but we had more robust and better results using the ray plane intersect and Cherukho board. But for projector, it's not that good. And also, it's not mentioned here, but we for the stereo calibration, gray patterns were also better. But both methods are still well enough for our point cloud and depth map reconstruction algorithm that Yuri was talking about. So some of the things that I want to tell you. So if you have the task to calibrate camera and projector, and so you would know some things that we did and we faced during our work, and try to meet them or mitigate them or something like that. So of course it should go without saying that calibration board should be as straight as possible. Crooked and warped board will yield very bad results in calibration wise. And yeah, and actual the first trick that we did was to glue the calibration pattern to the cardboard, and cardboard will only take you so far. After gluing it, start to warp, so the calibration results were not good. So in the end, we ordered the calibration board to be printed on the material called debond. So it is two parts aluminum sheets and I think PVC or something like that in between. So this was quite good, but still this material is not the best one for the calibration, since it is actually created to hold form after you force them to some position. So the best one yet that comes to my mind is 5 mm thick acrylic with some UV printing or something like that. I think will be the best solution. Of course, the mirror or something like that will be better, but it's quite brittle, so it's impossible to work with. Gamma correction. So when we tried to make some reconstruction with our board, we noticed this strange artifacts. So they were caused by the non-linearity in our luminance of the projector. So we needed to make some gamma correction to account for that. Yeah, and this step is actually mandatory, because for the our fringe pattern method, it should be done firsthand. And it's not only should be done not only for calibration purposes during the calibration, but also before reconstruction. Each pattern that is generated for the projectors should account for gamma. So we had our camera quality issues. As Yuri told, we are projecting sine or cosine wave onto our reconstruction scene. So we had some strange results for the reconstruction, but when we tried to plot the part of the sine wave that is captured by the camera, and we saw that our chip camera is basically clipping it. Even if we try to decrease the amplitude of the sine, we still had a lot of clipping. So the conclusion was that our chip camera, it's not good, at least for our method. I guess the grade code pattern should not suffer as much because of it, but in our fringe patterns we cannot afford to have square wave reproducing sine. So we actually did some experimentation. Of course, the best result we yield by the DSLR. It's almost one-to-one with the reference, I would say. But phone camera, it's also quite good, especially after the applying the median filter with some moderate kernel, like 5 on 5, or I think on phone we did 11. So yeah, the camera choice is quite crucial. Also, we don't have the result here, but we also are now working with the Z camera from Stereo Labs, and it should be quite better in that respect, since it is specialized part of equipment. Yeah, and about the projector, when we tried to make some calibration and actually construction, we saw that we got a beautiful rainbow in our images, and that was actually caused by the time multiplexing that is used by the DLP projector. So basically, how it works, the projector has the circular filter with 4 sectors. 3 of them is RGB, and last one is just blank. And the DLP projector, using the mirrors, is constructing the images from the individual colors on the plane. So not it's actually tricking our eyes, of course, and projecting one by one RGB frames. It can be mitigated by setting the exposure time to a multiple of projector refresh time. So if you have 60 hertz, so it should be 160th or 120th or something like that. But we also face some issues with our phone, because we could set 160th, but we didn't have 120th, and only 125, and on this exposure time, the rainbow appeared again, which actually interfered with our image reconstruction, since of course we had irregularities in our sine waves. But yeah, the better choice for this case will be the 3LCD projector, which is actually constructing the image from the RGB individual images in the projector and projecting the whole image as one frame using the prisms. So we are trying to get our hands on one of those and try it out in our work. And the last thing that we want to do, but it's not done yet, we have the turntable for the 3D reconstruction, and it should be also calibrated. It's now operated via IR remote, which is connected to our Jetson Nano, so we are using it for the calibration to turn our plane, but we also need to use some augmented reality markers to estimate the rotation of the turntable, which is actually quite interesting thing also, because when we will have those markers glued on the rotation on the turntable, we can project some points, or for example, if the user will need to calibrate cameras, we can in the system we can actually tell him how to place the board using the augmented reality markers. So it's actually a very cool thing to do also. So the things that I was talking about now we faced during our work. Hopefully, if you will have those kind of tasks, you will remember about what I was talking about and account for them, because we spent quite some time on some of these problems, and searching for solutions didn't yield much of the result. So we needed to think about how to mitigate them ourselves. So yeah, that's basically it from my side. And if you have some questions, please ask them. I will gladly answer.
Mm-hmm. Yeah, I can see that we have one question in the chat. Mhm. So maybe I'll read it. Regarding the problems you had with overexposure of the black background pattern, have you considered simply lighter than black background, standard 18% gray, for example?
Yeah, yeah, we did it actually, but it still wasn't enough because it still was overexposing, and in our case, it didn't yield much result. And the solution that we came up, I mean, the inversion and making the blob detector, is yield very good results for the calibration. So even we did even things like when the room is very dark and we need to calibrate our camera with the calibration board only, we even used our projector as a light source, as you said, the actually setting some 80% of the gray or something like that. We actually use less of the 80, but yeah, we did something like that, and it wasn't quite good for us. Okay, so maybe some other questions.
There's one in Q&A, and it's from Adam.
Yes, Q&A.
So what are the next steps?
So the basically next steps are, after we calibrate everything and calibrate our turntable, we will create this kind of the rig that will like make the automatic reconstruction and calibration. So as of now, our test rigs is consist of the projector and camera on tripods and actually turntable on a table, but we want to create some rig that will be can be transported and used for the 3D reconstruction. And for example, also we want to reconstruct some I don't know, artifacts or something like that, and try to 3D print them when the model will be a 3D model will be available. Yeah.
Hmm? Do we have anything else? Just
Did I actually answer the question, or
yeah.
can you put something like that? Yeah. Yes. Okay.
Great. Uh, so as I wrote in the chat, really feel free to ask any questions, because our R&D team has an amazing portfolio, amazing and very interesting projects. Like, for instance, Touch My Heart, the one I wrote about. But for instance, there's also HR Molecular, which is a combination of artificial intelligence and extended reality that provides users with an easier and quicker way to create, visualize, and explore the nuances of molecular structure in one solution. So actually, it can help visualize molecules. So this is pretty great. And of course, if you'd like to learn more about what they do, just you can check out the R&D website.
Can I actually comment one thing about this question that I was answering about
Mhm.
light gray? As the problem also was that when you are creating the black circles on white plane for the calibration, they will not be actually black, because projector cannot subtract light from the board, so they will be uh, grayish or something like that. But when you are making the inversion of the pattern, you will have very well lit white circles. So they are quite easily to be digested by the blob detector in the OpenCV. This is also one thing that should be taken into consideration. Thank you. I'm sorry that I interrupted you, but it should be answered.
No, that's great. Mm-hmm. Mm-hmm. Okay. Mm-hmm. So I see that we've got another question. So how often do you organize such meetups? So this is actually the first one, first R&D meetup, but next week, 10th of December, we're going to be speakers at the game dev meetup. We're going to have two lectures there. First, it's molecular MR multiplier, a cross-platform, collaborative interactive game for scientists, and then analysis of seismic data in VR using the Unity 3D engine. So it's a game developer meetup online. It starts at 6:30, December 10th. So if you'd like to join, I'll leave the link in the chat. Mm-hmm. Okay. So can we proceed with another presentation? Mm-hmm. Okay. So last but not least, we've got Vlad with neural network optimization. A few words about our speaker. So he's a research engineer experienced in the field of computer vision, deep learning, signal and image processing. He has worked on different challenging projects, including digital holography, compressive sensing, neural networks for 3D reconstructions. Sorry. So the floor is yours.
Okay, thank you. Hello, everyone. Today I will talk about neural network optimization and a few more words about me. I'm highly interested in computer vision for both 2D and 3D and mostly focused on edge devices. And since almost all neural networks take a high amount of time to compute, it is required to apply some optimization to increase the performance of neural networks and the whole system. And today I will give some insights into the neural network optimizations and some features and methods that I have used and faced during my work. So basically there are three different types of hardware for neural network training and inference. Such as CPU, GPU, and hardware specifically designed for neural network inference and training, like TPU from Google, and different mobile neural processing units. And mostly I will focus today on CPU and GPU since they are more popular and more widespread and used almost in every device. CPU is a more widespread platform, and it has some features like SIMD and fused multiply add that can provide very fast and high performance. SIMD stands for single instruction multiple data. As it says, we can apply the same operation to the different data. So basically we used data parallelism here. However, we can't apply different operations to the same data, and it means that we don't use any concurrency here. And fuse multiply add, it's a floating point multiplication addition operation that is performed in one step with a single rounding operation in the end. Also, CPU is more flexible for developing and prototyping. Some unique operations that are used in neural networks should be added manually to a lot of different frameworks. So it's more simpler on CPU add these operations, and also it's default choice for small size models. Contrary, GPU has more logical cores than CPU. It provides high optimization through data parallelization and operation parallelization, and has very high throughput. However, single GPU core much slower than CPU, and the high throughput is guaranteed by a lot of cores in GPU. Also, GPU performs work much more efficiently than CPU, which is kind of trend nowadays in neural networks training. It should be green and very power efficient. And also, I would recommend to use GPU for middle size and very large models with lots of operations. So basically, there are two different types of optimizations that we can apply to neural networks. Graph optimization and operation optimization. So one of the main operation is convolution. This operation is kind of the main operation in computer vision and especially convolutional neural networks. The main goal of this operation is to extract some features from the image. It's basically done by applying some filter over the image. You can, by specifying special weights on this kernel filter, you can detect different features, so for example, edges, or perform different operations like sharpening or smoothing the image. By combining several convolutional layers, we can construct convolutional neural networks. However, typical convolutional neural networks consist not only of convolutional layers, but also there are different other normalization layers, nonlinear layers, and etc. These layers allows convolutional neural networks train better, give better accuracy, and so on. However, the convolution operation itself is very expensive in terms of time. So from these charts, you may see that the time taken by each operation in the typical convolution neural network. Basically, convolution operation takes almost 85% of overall time. So probably the most obvious step in the neural network optimization is to optimize convolution operation itself. So there are basically a lot of different algorithms for convolution optimization, but three of them are the most popular. It's GEM, Fourier, and Vinograd. Let's start from the GEM algorithm. So basically, the image is presented as a three-dimensional array with RGB channels, red, green, blue. And the image size here is just 4 by 4 for simplicity. And we apply convolution, this orange filter, to the image with size 2 by 2. And here we have step size equals 1. So we move this filter over the image with a step equals 1. The gem algorithm is based on the image to column and image to row function. So basically they transform the image part of the image to the respective row or column. And we proceed with such operation over the whole image and move this whole image to the two-dimensional array. Also, we transform the kernel to the two-dimensional to the one-dimensional array. So here we have small kernel. We have 2D image. Image transformed to 2D, and we perform matrix multiplication, just one single matrix multiplication, and receive some one-dimensional matrix, which we then convert to the required shape and receive the output. So basically, what's gem like more concrete, we just replace a lot of different small matrix multiplications, a lot of operations into just one big matrix multiplication. Almost similar idea is used in the Fourier algorithm. We have here our input image. We have a kernel which we want to use for the input image. We transform the input image in the Fourier domain. We also transform kernel in the Fourier domain. Then we multiply these two images element-wise in the Fourier domain, obtain two-dimensional matrix, and then convert this matrix back to the spatial domain and obtain the result of the convolution. And the last one is Vinograd. The approach is also very similar to Fourier and GEM. So basically, we have a Vinograd domain here, and we take some part of the image. We take filter and convert both part of the image and filter to the Fourier domain, Vinograd domain. So in the Vinograd domain, we have two matrices of the same size. Here we have also element-wise multiplication, and we obtain the result matrix in the Vinograd domain, and this matrix is converted back to the original domain, spatial domain, and we obtain the result. Which method to choose mostly depends on the specific platform you choose, and usually this kind of optimized algorithm are already implemented in the hardware-specific libraries. Another class of optimization is data layout optimization, graph optimization. And the first thing you may try with neural network is to change data layout. Data layout usually affects on how data is stored in the memory. For example, for NHWC layout, firstly, I should mention what is NHWC. So basically, we have a four-dimensional matrix where N is batch size, H and W is height and width of the image, and C is number of channel in this image. So basically, for this case, the first pixel of each channel will be in the same, will be nearby the previous pixel. So basically, the last index in the layout type specifies which pixel will be nearby in the memory. The best data layout usually depends on type of the optimization for convolution you use. And the correct data layout usually used to optimize memory manipulation and not to lose time to access the different parts of the data. So for example, if we use first data layout, however, we need using our convolution operation, we need to access not first pixel, but we need to access the 20th pixel. We need to, it will take more time to access this data. When data goes through the neural network, its shape usually changes. And the operation with relation to data shape change can be divided into three main groups. It's a layout obvious operation, which doesn't affect in any manner. It doesn't matter for this operation what is the shape of the data. So it's usually it's activation functions like ReLU or softmax. Layout tolerant operations, it's operations which are usually hard coded by the like is not very affected by the shape of the data itself, but the shape of the data is changing. And layout dependent, it's usually hard coded by the user, by the programmer, and we change the shape of the data completely. And usually in the optimization library, there are some specific functions for each data layout. And for example, on the image on the right, you may see that here we have some convolution operation for specific layout and for specific number of channels in the image. And this allows to write more efficient code, and the operation proceeds faster. And also it's a good manner to use number of channels in divided by 8 or 16. Another type of operation optimization, it's operation fusion. We can fuse multiple operations into a single function without saving some intermediate steps of the calculation. This optimization enables better sharing of computation, remove some intermediate allocations in memory which may appear, and reduce some time required for launching this some functions and data which is required for each operation. The operations can be classified into 4 categories. Injective, where we map one value to another. Reduction, where the reduced number of input data. Some complex out fusible operation, and opaque. When these operators are defined, the compiler usually categorize each operation, and some operations can be fused. For example, we can fuse one injective operation into another, or a reduction operation can be fused with some input injective operation, and so on. According to this, we can usually fuse all operations conveniently. And for example, we have a convolutional layer here with some input image and filter. And afterwards, we have some bias addition operation. And what compiler usually does, it just converts these two operations into a single one. And the advantage of this is that we don't need to wait for the next operation to perform, and we don't need to allocate some new memory for this function to run. Another approach for model optimization is to use some lower precision than float 32-bit. For example, mixed precision or float 16-bit. It is possible to use this precision during training or inference. Typically, with mixed precision, we can achieve up to 4 times speed up in cost of time and 2 times memory size decrease of the neural network. Most deep learning frameworks support this feature as easy to use, and we can use it and just receive some speed up. And the main advantage also of the mixed precision is that usually the accuracy of the algorithm is not changing from when we're moving from float 32 to the mixed precision. Also, we can achieve some more optimization using even lower precision, like integer. We can use int 8, int 4, or even binary networks. However, this reduction in precision usually leads to some lower precision, and it usually could be a challenge to train a very efficient neural network with such low precision. However, the speed up we can gain is very high, and sometimes here we have a trade-off between the speed and accuracy we want to achieve. And the last option for neural network optimization is pruning. So it's basically dropping some weights of the neural network. There are 2 main approaches for pruning. We have structured and unstructured pruning. Structured pruning allows to just remove some blocks of the neural networks, like some channels of the convolutional neural network, some part of the other layers, and usually it's not just a random process, and we remove some weights that doesn't affect the neural network very much. So also you may see on the charts, on the plots here, that on the x-axis is percentage of weights which is remaining in the neural network, and we can drop the percentage of weights up to 7% even without losing accuracy a lot, which a very good speed up. However, this area is also still under development, and it's very popular in the scientific community. And the last part of my talk is about how to use all these optimizations for neural networks. Luckily, there are a lot of already developed tools for doing such optimizations. There are TVM, TensorRT, and many others. So what is TVM? It's a recently developed optimization library for neural network optimization. It supports different platforms, mobile, GPU, CPU. It supports also different frameworks, Kefi, TensorFlow, MXNet, and so on. It performs operation optimization, graph optimization, and the core feature which I would kind of recommend to use is Auto TVM, which searches the best parameter of best configuration of optimization options for your model to gain the best accuracy and the lowest speed for your network and the platform you select. Usually it outperforms standard approaches of different standard tools and approaches of different libraries for different platforms. So on the plot on the left, you may see that it outperforms TensorFlow Lite on CPU. This one plot is for CPU for different neural networks. And also it outperforms TensorFlow and MXNet optimization for GPU. TensorRT is another library for neural network optimization. This framework supports also multiple deep learning libraries like TensorFlow, PyTorch, and even ONX format. This framework provides layer and tensor fusion, weights and activation, some management. Also, it provides some optimization to memory layout and allows to execute your model in multiple streams on CUDA. And I should mention also that TensorRT is a library that was created by NVIDIA and mostly focused on optimization for GPU and for various types of GPU. This library shows very good performance increase for different neural networks. It works even better in most cases for GPU, even better than TVM. It supports different type of precision like float 32, float 16, mixed precision, int 80 and int 8. And there are also a lot of additional features like data loading, working with video stream, and so on. And to sum everything up, so I would recommend to use TVM as a default choice that for optimization of the neural network, since it supports different platforms and usually easy to go. And after TVM is very interesting feature of this library, which can significantly reduce the execution time of your neural network. And for better optimization for each platform you select, it's better to use libraries that were developed specifically for this hardware, like TensorRT for GPU or Intel MKL for CPU. It's better to select which platform or hardware you will run before you will design your model, because it is required to look what operations usually are supported by each platform, because I faced some problem when we tried to port model from one platform to another, because some operations were not supported and it was required to write everything manually. And it's kind of good approach to optimize your model is to use some quantization or mixed precision during training, because it mostly will not affect your accuracy of the model. Because if you will try to do quantization or pooling afterwards, like for trained model, it will decrease the performance of the model. So basically that's all. Thank you for your attention, and if you have any question, you may answer.
Okay, so do we have any other questions? you can actually ask questions to all of our speakers. They are all still with us and happy to share their knowledge. So if you have any questions concerning our first presentation or second, third, just feel free to ask. Or if you'd like to know something about our projects, what we work on, what actually our R&D team does, what are the challenges they're facing up right now, or they face up like every day. So if you want to know, they're here for you. Or if not, you can also send us any questions if they pop up into your mind after the meetup. I'll share our email, or maybe guys will share email directly to their team. You can always contact our speakers on LinkedIn. I also shared the website of our R&D team with their projects, also with job offers if some of you would like to join our company and this great team. And also, as I mentioned, next week our speakers, our experts, will be speaking at another event that would be a game developer meetup. I also shared the link in the chat, so if you'd like to see us live once again, we'll be very happy to see you again. So just register and see you there next week. Okay, so maybe our speakers, maybe you'd like to add something or ask some questions, or no? Okay. So as I also said in the beginning, a recorded version of this webinar will be this meetup will be sent to you later on, hopefully tomorrow. So thank you guys very much for sharing your knowledge with us. I think it was really impressive, and it was a great experience for everyone. Also, I'd like to thank everyone for your participation and for being with us tonight. So we really hope that you had great time and you enjoyed the experience. And if you're interested in our upcoming events, check out our Facebook or follow us on meetup.com or Instagram or on YouTube. We are actually quite active on social media, and we're also very happy to share our knowledge and expertise with you. So if there's no more questions, I think we can call it a day. And once again, thank you very much for your participation and for this huge dose of knowledge that we had the chance to receive this evening.
Yeah, thank you. Thank you for your time.
Thanks.
Have a nice evening.
Thanks. Bye bye.
Okay.
Thank you.
Thank you.
Bye-bye.
Have a nice
Bye.
evening.